I have to go actually. So I will just quickly tell you, I think Dipankar already introduced you about the Aditya-L1 mission, right? So there are several payloads. I mean, I will share the entire presentation. Don't worry about it, but I won't be able to cover everything here. So my job is to introduce the VELC. VELC is, what is VELC? Yes, exactly. So so I will talking about VELC, and then what are its capabilities, what can be done. Okay, very quickly. How it will be done, not going to tell you. Maybe you can discuss with me later on. So here, this is the image. The red color that is shown is the field of view of LASCO C2. LASCO C2 field of view starts from the 2 solar radii approximate. So the problem was that what is happening inside the 2 solar radii, we didn't know till now. We knew it using other spacecraft such as stereo, which was looking from other vantage point, but then there were a lot of scattered light. So we still do not have much information what is happening inside this. So the field of view that you see in the, I mean, this is the image inside this red image is not the real image. Okay, there's something that I have put up here, and this field of view is the field of view of Aditya. VELC field of view. So you can see the VELC field of view start from very close to the sun, 1.05 R0, all the way up to 3 R0. Okay, 3 solar radii. And this LASCO C2 start from 2 solar radii. Okay, so then that means that with Aditya, we will have an information about what is happening inside the inner corona. What is happening inside the, what is happening below 2 R0, how the corona is behaving below 2 R0. That is not, which was not accessible till now. Now in VELC, we have two things. We have imaging as well as we have spectroscopy. Okay, so the imaging is all the way up to 1.05, all the way up to 3 solar radii, while the spectroscopy is only up to 1.5 solar radii. So you can see that we have different slits here. For spectroscopy, you need slits. Okay, so so we have 4 slits. So it is a multi-slit spectrograph. And then with the spectroscopy, we can also study Doppler motions, as well as we can compute density, temperatures, and other things, right? Depending on the line that we are going to use. So we have both imaging as well as spectroscopy, imaging up to 3, spectroscopy up to 1.5 solar radii. Okay. So if someday, if the data will be available to the community, and if we overlay a VELC image with the LASCO image, this is how it will look. Okay, but right now it is not possible. So I mean, this is a cartoon that I have put it up here. Okay. Okay. These are old numbers, but this I hope will be revised once we have once it will be flown into space, and after the calibration, these numbers will be revised. But more or less, the spatial resolution is 2.5 arc-second. Cadence is approximately 1 second. We can go up to 1 second, but definitely will not get the cadence of 1 second. We will probably get the cadence in minutes in white light, because all these things, continue to change throughout the mission. And I think this, I don't know, this presentation is, I think, quite old. So these are old numbers, but these will be updated. But don't think that whatever I have written here is you should be getting it. I may not be. Okay, it could be easily to 1 to 4 minutes can be changed here. Spatial resolution spectroscope is 1.25 arc-second, but to build a signal, sometimes we average along several pixels. So probably you may not get this type of resolution in spectroscopic channel also. Okay. Anyway, but these are some of the instrument characteristics, and I have already told you that it will be useful for white light stage. So white light means always the continuum. I mean, we are not looking at a particular spectral line. We have a wide band around 5,000 angstrom. And then we are looking at that band, so that we call it as a white light, because it has like several, it encompasses several angstroms. So why you wanted to study the inner corona, right? That is the first thing that we should be asking ourselves, why the inner corona is important. So here is the plot by Zheng and Derek 2006, where they have shown that usually the CME velocity, which is shown in the blue, and X-ray flux, which is shown in the red. Probably you must have already read about the X-ray and X-ray flux in the Srikar talk. So what happens is that usually they are correlated, not very well, but in some CMEs, they are very well correlated. So they have shown that X-ray flux has different stages, slow rise and then the fast rise and then a decaying phase in the X-ray flux. Similarly, the CME velocities have different stages, onset, slow rise, fast rise, and then the speeds become more or less constant. Now, this is schematic diagram. I mean, not all the CMEs behave in this way. I mean, CMEs are very variable. I mean, they continue to accelerate all the way up to larger heights. But impulsive acceleration somewhere happens in the inner corona. I mean, this part happens in the inner corona between less than 3 R0, 3 solar radii. Okay, so that is the advantage of inner corona. So you see that there are different forces that happens on the CME. You have already read about the CME. I think Shatabdi has already covered this. So you of course have a gravitational force, and the CME is not just it is a plasma with a helical flux slope. So it will also have a Lorentz force. You remember in the equation, in the momentum equation, you have J cross B. So you have Lorentz force also. So, and then you have a drag force because it is moving through the solar wind. So it has to pass through the solar wind. So there will be a drag which will be acting on the CME, right? But these different forces are not, I mean, they are acting at the same time, but different forces dominate at different distances. For example, if you are very near to the sun, what happens that the CME, the Lorentz force dominate because of course it is an electromagnetic force, J cross B. It will anyway dominate over gravitational force. But what happens as the CME is trying to expand, and you remember what is the solar wind solution? The solar wind solution increases and then the solar wind velocity increases and then it saturates up to 400 km/s, assuming they are the thermal winds. I'm not including additional complexities, right? So very close to the sun, the solar wind velocities are very small. Okay, as well as but the J cross B, the Lorentz force is actually quite large. So during its initial during the initial time, the Lorentz force is actually dominates. Okay, and that actually accelerates the CME. But what happens as the CME gets as it moves outward, it expands. Now you must have already read. If it expands, assuming that there is no flux injection, there is no flux expulsion, what will happen? The B will dilute. Of course, B will dilute because spatially it is extending, right? So the B will go down. So J cross B will go down. So eventually the Lorentz force will go down. So and then solar wind is picking up. So at some point, the Lorentz force will go down and the drag force will increase. And that's why the drag force starts acting at a later stage. Initial stage, the Lorentz force is the gravitational force happens all the time, but it's not really important. So what is this critical height? Okay, what is this critical height where this impulsive acceleration is seen? That is very, very difficult to model. That we still do not know. So that is something happens in the inner corona. And here is what would be the significance of VELC. With the VELC, with the high cadence white light data, provided it is high cadence, we will be able to determine precisely the height of sudden change in slope in VT profile. Right now, there are 1 or 2 points here. Suppose after the launch of Aditya with 1 second cadence, you have like thousands of points here. Then you will be easily model and properly fit it and then find where is this initial extent happen. This is very important for the reconnection model because it tells you where the reconnection is happening, at what heights the acceleration of the CME is happening, at what heights the Lorentz force is maximum. So all these things are still unknown. So that is like one significance of the inner corona to understand the kinematics of the CME, to understand the role of these Lorentz forces in the inner corona. Okay, and of course we'll get the complementary data from Solex, which you have already done, as well as SUIT. SUIT talk is in the afternoon, so you should attend it. And with the SUIT also you can get, I mean that will complementary data. SUIT will complement the VELC in understanding the CME. So this is one example. These are from the existing observatories, these data points. But you see, they have just extrapolated it up to here, but there are no real data points. How do you know that they will follow this curve? We really do not know. So VELC will provide the data in this region. Okay, so that is like one significance of VELC. So it will improve our understanding of the CME initial variation, right? Okay, so this is again, you see, there's some studies have been done. So this is the inner corona from 0 to 2 R0. Some studies have been done, but these points are very variable, and for not all the CMEs you can get such a nice data. This is one of the very, very few CMEs out of thousands of CMEs that they could get such a nice plot, but not all the CMEs will behave like this. But with VELC, we'll be able to know whether all the CMEs behave like this or they have different acceleration or velocity profile, and that will also improve our numerical models that we are developing, because your initial acceleration of the CMEs depend on the initiation model of the CME, whether you are using a breakout model. I don't know whether Shatabdo has talked about the breakout model and other different type of models, the models of CME initiation, how the CME initiate, right? So there has to be some reconnection happening somewhere, right? So these acceleration profile tells you where the reconnection would happen, how the CME will initially accelerate. Okay, so that's why these information are important. So it has been done before, but this is one. So you see this paper is from 2007, and after that I have hardly seen any other paper showing such a nice plots of the CME. So it is one of once a blue moon phenomena. Okay, so this way the Lorentz force act. So this is something that Shatabdo and we have been doing in 2020. So what we have been doing is we decided to use the data from the stereo, which goes up to 1.5 solar radii, but not below it. So you can see there are some points below 2 solar radii, right? And we decided to, we thought that let us understand how the CMEs expand, or whether the CMEs do expand in the inner corona or not. What we found is that the CMEs expand, and this expansion actually goes away beyond 4 or 5 solar radii. After that, there is no expansion of the CME. Of course, the CME will expand, but their angular will remain the same. There is a spatial expansion, but not the expansion in the angular width. Okay. Why there is a spatial expansion? Because if you continue to increase the radius, of course, the r d theta will continue to increase, your extension will, spatial expansion will be happening, but not the angular expansion. So angular expansion happening here. Question is why it is happening. There is still no model that can explain this. We still do not have any numeric. Go. Exactly. What is the time interval between two images? 2 dots. So here also you can see the problem is that one data set is here, another is here, another. It's a very, very poor cadence. Okay. 1 point is here, 1, 1. So 3, 4 points all the way from 2 to 4 are not. That is not acceptable. From 2 to 4 are not, if you have 100 points, then you can better understand this, what is happening. Okay. So, so this advantage will be there with VELC, but we could do whatever we had at that time. The best we could do, we did that. And then if you plot the histograms where this expansion will actually go away, you see it is peaking at 2.5 or not. So that is the height, critical height according to us, where the CME expansion is ceasing. I mean, it is not happening after that. Or where the CME expansion is maximum, it is 2.5 R naught. And that is based on the existing data. What we do not know is what will happen if you have a better data set, and whether you can get a, whether this plot can be revised or not. So that is something that we still do not know. Probably after the launch of VELC, we'll be able to do. So all these things I have already said. Just when you read this presentation, you can do it. So there are some CMEs. Not sure whether he talked about the still CMEs or not. Shatabdo, he talked about still CMEs, right? Okay, fine. So there are some CMEs which do not have visible signatures in the on the disk. For example, there was a CME associated with it, but you can see very nice signatures here, right? But there was CME here also. Where is the CME? You don't know. But you can't, because you can't see anything, but it was supposed to be here. But here you know where is the CME. It should be in this direction, and that's where it is. So this type of CME are known as tilt CMEs. That means you can't see their signatures in the on-disk images, but you see them in the coronagraphs. The question is from where they are coming. The problem is that the field of view of these images are only up to 1.5 solar radii. And the field of view of there starts from 2 solar radii. So what is happening between 1.5 and 2 is something which is missing. Right. So in order to probe the origin of these type of CMEs, you need the data set that can probe the inner core. Right. I think that's clear. Let's not go into. So it has been shown, for example, this is the ground-based coronagraph, which has the similar field of view as Aditya. But our Aditya will give more better data because it is up in the space, not at the Earth. But here you can see that these type of CMEs are actually not starting from here. They are actually starting from here. You can see a little bit bright emission here. So these CMEs are actually, you will not see anything. They might start from here. And then you will see them in the coronagraph. So question is, what spatial is happening here? But the problem is that they couldn't study it. Why? Because it was towards the edge of the field of view, and after few frames, the image, they couldn't see anything. So imagine if you have this all the way up to here, and then you would be able to properly study these phenomena. So these are known as still CME. The question is whether the magnetic reconnection is happening at these higher heights. It has not been expected, but it seems it is. The question is how to model it, and what is the model for that? We still do not know. So these are the questions that you can answer with VELC. Okay, let us. These are the numerical simulations, and in the numerical simulations also it has been predicted. For example, there is a main CME which happens, and after that, a small CME is actually starting from here, much away from the disk of the sun. Now these are not the real observation. These are the numerical simulation. The question is whether this phenomenon is happening in reality or not. So you need a data, you need an instrument that can image from 1 all the way up to 3 R0, because that's where they start at the 2 R0, right? So which is not possible from the current instruments. So I mean, there are models, but whether they are correct or not, we'll be able to verify it using Aditya. What is the signal? Okay, so the contemporary views of CME is that CMEs has 3-part structure. Okay, but this you must have already read, but not all the CMEs have 3-part structure. Some CMEs do not have. So the question is, and it has also been shown that the core of the CME, this core, is usually a prominence material. Prominence is the cool material, and that's why it appears bright. It's because it's very dense, so it can scatter more disk light. So it appears very, very bright. The question is that people used to believe that it is a prominence material which is cool, but this is not the case now, because when you measure, when the CME reached at Earth and people have started measuring the temperatures of this region and this region, then they found that only 4 CME shows the signatures of low temperature. What about other 96% of the CME? So the question is whether the CME core is really a prominence, or it is something else, or it's just a line of sight effect. Or if it is a prominence, where is that material going? Okay, is it falling back, or it is being carried away all the way up to all that we still do not know. So so you need to know the origin of these bright material, bright feature here. So then you need a data set which is here. You need a data from this region, which is right now not present, that where this bright feature which is seen here, where it is forming. It is a really prominence material. It's just a hot flux probe, and then because of the line of sight effect, you see these things. So maybe 10 minutes. Because I also have to go there. Students might be waiting also. Yeah. No. Let me complete it. And then, so you see that to understand the origin of those bright emission, you need to understand. You need to image the inner corona. Similarly, if you look at this image, you see the CME is here. Okay, but if you look at the disk, you see that the magnetic reconnection was happening here. And if you extrapolate it back, it will be here. So why is there a displacement from here to here? So we know that most of the CMEs get deflected like this. So where is that deflection happening? So to understand that there is no data present here, you need an inner coronagraph, right? In order to understand how this deflection is happening. So that is another significance of inner corona, why we need VELC. Okay, so it changes the direction of CME. So this is one of the paper by Howard. Now he has suggested it, not verified it, because we do not have information of inner corona. He said that the bright emission that you see here is just the reconfiguration of the magnetic flux probe. And because of the line of sight effect, you sometimes see bright emission, sometimes you do not see. But whether it is really the case or not, you need to understand where these bright features are forming. And for that, you need the inner coronagraph. That's what VELC will do. Also, as I said, we also have a spectrograph, right? Multi-stage. So we can also study the spectral features of the CME. What does the spectra give you? It gives you the Doppler velocity. It also gives you the information of the thermodynamic properties, such as density, temperatures, right? So, okay, sorry. Let this, I think, slide summarize everything. If you need the kinematics, if you need the white light observation, you can I mean, the kinematics is determined by the line of sight velocities, which is given by Doppler velocities, which is given by the spectrograph. Plane of sky velocities will be given by coronagraph, white light coronagraph. If you combine these two, you will get a 3D structure, 3D velocity structure of the CME. That's where it is important. Morphology of the CME is 3D reconstruction you can do using line of sight and the plane of sky velocities, right? Similarly, you can study the expansion. Right now, the expansion that we have studied, remember I told you the graph where the CMEs were expanding. Those expansion was in the plane of sky, right? So it is expanding like this. But who knows, it could also be expanding like this, right? And how do you see this expansion? You see this expansion in the spectra. So those things also you can study with the spectroscopy. So it is very, very useful for kinematics. It can also be useful for thermodynamics. Why? Because with the spectroscopy, you can use the density diagnostic. You can compute the densities. You can compute the temperatures. You can compute the composition depending on the lines that you see, right? So that is the advantage of spectroscopy. And people have done it before, but with other lines, we will be using a different line. Let me not go here, but this is a very big presentation. Yeah, let's not go here. So, for example, if you see these eclipse images, you can see if you put a slits here, then you can see these different lines: iron 14, magnesium 1, again iron 14, helium 1. So it tells you that the plasma is multithermal, because at the same time you have iron 14 also, as well as the emission from helium. Okay, so they said that the signature of helium is because of the presence of the cool material. That is the prominence material again. But the question still remains the same, because eclipse only stay for 5 minutes or less. So you can't study much dynamics. But assuming that you have similar type of data set 24/7, you can actually study what is happening to all these material or all these lines, how they behave in time. And then that's where you can answer what is happening to the prominence material if it is present. And then what is the reason of that bright emission that you see as the core of the CME, right? With the spectroscopy, you will be able to answer. Okay, so as I said, the different lines is indicative of the cool chromospheric plasma. But then where is this plasma going? So this is the other image of VELC. So this is done by Tanmay. So these three are not option. Now I have superimposed it over the eclipse image. So up to here, we'll be able to see from white light, and up to here, we'll be able to do from the spectrograph. Whereas spectrograph is not going all the way up to 3 R0, because the signal to noise also decreases. So we have kept it only up to 1.5. So how the CME, so this is a study that we have been doing. Some of you are doing project with Jyoti, right? Okay. And she was doing this work, and we have seen that what we have found is, using the existing instrument, that the temperature of the CME is not changing as it's moving outward. And the core of the CME was not the prominence material, it was a hot plasma. So the question is, but that was only for one CME event. So of course, now we are doing the statistical study, whether all CMEs are behaving like this, or if some CMEs do have prominence material, where that prominence material is going. So we are doing those studies, but with Aditya, it can be done even with a better cadence. So this is, so not only, so this is the temperature coverage. So you know that a different wavelengths, also different lines are formed at different temperatures, right? Okay. So if you see, the VELC will be covering these temperatures, 6.12, 6.25, 6.30. But there are other spacecrafts also, UCOMP and DKIST, that are coming. And there's a UCOMP which will go up to a lower temperatures. And then there is a METIS and solar orbiter, which will going even up to the load. So what I'm saying is, not only Aditya, but if you combine Aditya with other observatories, you can actually study different temperatures and their evolution with time. So Aditya filled this gap here. This is, let me tell you, I mean, Aditya was planned before these two, but somehow we got late. So now these three are also there. But the good thing is that both of them are ground-based, and we are going to space. So we will have much better signal to noise, much better data set. So we still have some novelty. Yeah. So yeah, these are the things that I have said, that these you can do. These are some of the ideas that you can pursue. But yeah, provided you get the data set. Okay, okay, these so as I said, so these are some of an example of the MHD waves. So here you can see the transverse wave moving like this, like a string. You see this one here, right? So these are transverse wave. So what wave it should be? Yeah, it's similar to elephant waves only. I mean, really, they're called as kink waves, but they are similar to elephant waves. So I'm not going into what is kink wave or not. So these type of these signatures can be obtained in the line widths of this of the spectra. So if you can see such a variation in the line width, you can these are probable indicators or indirect signatures of these waves. So these line widths you can get from the VELC spectrograph, right? So then you can study those, as well as you can study slow waves. Krishna is expert in these, so I'm not going here. What I'm trying to say is that this is like one example of the comp, and here these are the Doppler velocities, right? So you can see that something is moving outward from here as well as from here, and something is moving outward, right? If you see these movies nicely from the both sides, things are moving outward. So these are waves basically. Okay, so probably from Aditya, we cannot say, but probably from Aditya spectra, if you compute the Doppler velocities, you might also get these propagating Doppler velocity features, which is the indicative of elephant waves in the solar corona. So these guys call them as elephant waves, although these were elephanic waves, but this is a very famous paper in 2007. So all these studies can be done. So I'm not going here. What else can be done? Okay, this is a really big presentation. So I will I mean, these are the last few takeaways. I will share the presentation with you. Okay. So VLC will take the images of solar corona with high spatial and temporal resolution. Aditya will provide opportunity for rigorous studies of the CME. Aditya is capable of multi-speed spectroscopy. Therefore, it is capable of I mean, it can be used to understand the thermodynamic evolution. It will allow us to understand the initiation mechanism. As I said, initially, what are the acceleration and what are the velocity profiles? Based on that, you can define your initiation mechanisms, physics of the propagation of CMEs in the inner corona. It will also help us to understand propagation of transverse waves, because as I have told you, the waves are seen in the Doppler velocities, and you will get Doppler velocities from the spectrograph. So it will also help us in estimating the transverse waves and the energy flux. And of course, we have a temperature sensitive lines, because we have three different, I think Dipankar would have already told you, in VELC, we have three different iron lines. So those two of them are temperature sensitive. So it can be used to diagnose the plasma properties, specifically the temperature. It can be used. Yeah, so that's overall. So I think VLC will be a very interesting instrument for future, and it can be used for many studies. So yeah, so that's it. Sorry, I'm not able to complete everything because I have to rush for the interview. So, but anyway, if you have any problems, you can. I'm here this week, so you can also come to my office and discuss. Yeah.
Okay, let's thank Vaibhav.
Thank you.
Then we can have questions.
Yeah.
Of course, Vaibhav will be here around, so you can discuss even afterwards. But you can ask one or two questions, and then we can break for tea.
Sir, is VLC a narrowband coronagraph, or it has a wider band than other? Like LASCO C2 is narrowband.
It is a narrowband. It's not very wide. It's around 5,000 angstrom. I forgot the bandwidth. I will check and let you know the exact number.
And is same with the spectrograph, or it will
No,
be
spectrograph.
It will
There's
be
no band.
spectrum of the continuum.
Sorry, you get the
of the whole spectra of the sun.
No, you will not get the whole spectra. So we have, for example, we have these three spectral lines. Let me go to 5. Yeah. So in the 1 or 2 lines in the entire data, as well as we also have a pre-filter, which will filter only the, which will only allow the lines within a particular passband to pass through. So you will only see a couple of lines, not more than that, as he's pointing it out. So we are studying 3 lines: iron 13, iron 14, and iron 11, right? Iron 11, yeah. So only 3 lines we are studying. Iron 10 or 11, yeah.
Thank you, sir.
Yeah, but the main point is that the entire spectrum cannot be accommodated in the. In this.
More questions? Okay, if not, let's thank Vaibhav again and then let's
Okay.
break for.
Thank you.